problem, no problem. Were you able to register for Zoom?
Yes. So at NASA, we don't normally use Zoom, so it's just going to need to be.
Not a problem, not a problem. We have Patrick here, we have Anne here. Nice meeting both of you. All right, and let me just give a short introduction and then we can get started.
Sure.
Sure. We have so many people waiting to hear from you. So we are so excited. All right, I think time is 10:02, so let's get started. And are you okay with us recording the event?
Yeah, that's fine.
All right, thank you so much. Thank you so much. All right, so good morning, everyone. I hope all of you are having a great start to the day. Okay, so my name is Sajul James. I'm a faculty in the Mechanical Engineering Department here at Cal State Fullerton. And today we have gathered here for a workshop about learning CubeSat technology. I would say NASA CubeSat technology. All right, so first of all, I would like to welcome all of you to this technology talk event. And thank you for taking your valuable time on Friday morning and coming and attending to this event. A little bit about the organizers. So the event is organized jointly by the Center for Collaborative Research and Prototype Development, CCRPD, and the TitanSat student organization at the College of Engineering and Computer Science, ECS. And those who are unfamiliar with CCRPD, this center was established in 2016, and this center, CCRPD, promotes and also provides support for collaborative projects, particularly research projects among ECS faculty and students. The center also partners with local businesses, industries for conducting research, trainings, workshops, events like this, senior design projects in our college. Dr. John Fowler from Computer Engineering and I'm from Mechanical Engineering. We are the co-directors of the center. Coming to today's event, we will have the talk by NASA scientist Anne Nguyen. And this will be followed by a short presentation by the CSUF TitanSat student organization about their ongoing project on CubeSat. With that said, let me give a short introduction about the speaker for today. Anne Nguyen, she's coming from NASA. She's a mission architect in the mission design division at the NASA Ames Research Center in the Northern California, and holds a master's degree as well as a PhD degree in aerospace engineering from University of Florida. And her PhD research focused on small satellite technologies for precision drag-free control and drag force recovery. And Anne's work at NASA Ames Research Center includes mission architecture and design, project management, systems engineering, and subject matter expertise in guidance, navigation, and control systems of small satellites. All right, so that being said, without further delay, I would like to welcome Anne to give the talk. I hope all of you enjoy this event. Please feel free to post your questions or comments in the chat window and make the event as interactive as possible. We hope you will stay until the end of the event. I think that's all. We would like to welcome Anne to our campus and give this talk to our students and faculty. Welcome, Anne. The floor is yours.
Yeah, thank you so much for the introduction. And so if I talk too quickly, please feel free to let me know to slow down, and feel free to post your questions in the chat, or just feel free to come on if you have any questions. So today I'll talk about NASA CubeSats and kind of particularly what I do and what we do at NASA Ames and specialize in. So hopefully you guys can see my screen.
Sure.
Okay, yeah. So about me, I have my PhD in aerospace engineering with a focus in dynamics and control of precision space systems. And I have my undergraduate in computer engineering. And so I've actually been working at NASA Ames since 2015. I started as an intern, like all people that usually work at NASA. I started in the Mission Design Center as a subject matter expert in guidance, navigation, and control. And then I started moving towards kind of bigger studies. So I also work in the NASA Earth Science Decadal Survey designated observables for small sat mission architectures. These are typically architectures that are very, very large, multi, million, hundreds of millions of dollars. a lot of the focus is saying, a lot of these small sats have utility. What can we do to lower the cost by introducing these small sats into these what are typically, traditionally larger monolithic satellites. So I advise on surface biology and geology studies, as well as the surface deformation and change study. So, our CubeSats fly, every, 6 to 18 months. The study alone, just to figure out what we're going to do for these two architectures, are 3 and 5 years respectively. So hopefully I'll see, some of them fly before I retire. But otherwise, my normal day-to-day job, I work as a project manager for a bunch of CubeSat technology demonstrations, which I'll talk about shortly. But I started as an intern, and my first one was the CubeSat handling and multi-precision time transfer, CHOMPT, with University of Florida. Then I did project management of KickSat 2, and that launched in 2019, and VREX that started in 2020 and actually launched this past January. And now I'm doing the Payload Accelerator for CubeSat Endeavor's PACE project at NASA STMD, Small Satellite Technology Mission Directorate Small Satellite Technology Program. And so, I'll talk about, just a few of my CubeSat studies, our CubeSat projects, just to kind of show you kind of the little things that I do. But I'll give you an introduction. So we have lots of different NASA sites. And so particularly mine is over at NASA Ames Research Center in Northern California, as you can see here. And there are NASA centers and research centers around the country. And it's actually pretty interesting to be able to travel around, meet new people, figure out what everyone else is doing, and collaborate. So just to give a introduction for spacecraft classes, if people aren't aware of what CubeSats are, is that, basically there's the large, medium, small, microsatellite, and CubeSats. So I'll go through kind of each of the individual ones. So what you can see here are the kind of large satellite ones, as we classify them. These are, the, hundreds of millions to $1 billion satellite missions. Takes about a decade for them to go from start to finish. So you can kind of see the Landsat on the right-hand side, and kind of the high resolution images that Landsat has produced. And I'm pretty sure you've seen many of the beautiful images that Landsat has produced, and is actually very useful for, kind of global understanding of the Earth's environment. So moving smaller is technically smaller, what they call medium, are still on the order of 1,000 kilogram satellites, and so these ones are similar to what you see as Kepler, and so Kepler actually made lots of great findings for potential habitable planets, and so you can see kind of the relative size of Kepler here, and then kind of moving to what we consider the small satellite, but it's still quite large. So these ones are on the order of 500 to 800 kilograms. And so you can see GRACE, this is the Gravity Recovering Climate Experiment. And this is a lot of what my dissertation was trying to get definitely not as high quality as you can see here, but kind of lower fidelity, but on a CubeSat level. And so GRACE actually maps the gravity of the Earth. And so, everyone is very, very aware that the polar ice caps are melting, but where is that water going? And how does that change seasonally? When what you can see here at the bottom is the Amazon flooding during the springtime. And so, overall, globally, where does it go when it's not there? What does it look like in the spring versus the winter? And, the distribution of water around the Earth, because water has, gravitational pull. If there's more water, you have a more gravitational pull, and that's kind of what we try to study here. So moving smaller, the microsatellite, which is still quite large, on the order of 100 to 300 kilograms. This is LADEE, the Lunar Atmosphere and Dust Environment Explorer. So this one was actually did laser comm and also impacted the moon and gathered some dust experiments. And you can see that here it's a little bit more manageable, more human-sized, but still quite large. And lastly, we get down to CubeSats. So what you can see here is PhoneSat, one of the key CubeSat technologies at NASA Ames that kind of propelled our excellence in there. And basically, it was it all started at Cal Poly Senlos Obispo, where they kind of said, what can we fly, and inspired NASA to fly PhoneSat, which, as you can see here, your phone has a really high processor, integrated IMU, kind of, and basically power distribution system, basically everything that you need to run a satellite, just in a very small form factor. You see how powerful your iPhones are now. And so we had a bunch of really enthusiastic engineers to say, will it fly? So it flew first suborbitally, just to see if the phone would survive the launch, and it did. It flew on a suborbital rocket. The chassis definitely did not survive impact, but the phone actually did, and they recovered all of the data that they measured. The IMU, accelerometer, and mag fields. So it's actually pretty interesting. Then they incrementally actually put one on orbit, which was pretty neat. And so that kind of shot off CubeSats at NASA Ames in particular. So the CubeSat standard, we call them units. They're on the order of 1, 3, 6, 12. There's even the 6 elongated, where it's at 3 by 1. And so in general, the relative size of this, if you kind of think about it, in relative terms, is that this is pretty much the size of a coffee cup. The 1U size is the size of a coffee cup. The 6U size is about the size of a coaster. And 12U is probably the size of a small microwave. But in general, these are very small, but very mighty. And it does come with its challenges of trying to pack everything in there, your science experiment, all the electronics you need to run the spacecraft, all the batteries. But it's quite fun because there are launches that go up every 6 months, as you see Spacex, probably even monthly. It's very cheap to get to space, and it's a very there's lots of utility, right? So it's cost effective. The smaller you are, the lower the launch cost, because you mostly pay per kilogram, and you can always get on as a secondary. So when one of the larger missions are going up, they have a little bit of reserve kind of around the extra mass that's available that the rocket can lift. So they'll pop on a bunch of CubeSats as secondaries to these, larger satellites. There's shorter development times, right? So, the faster that you can get on orbit, and how small these projects are, you actually have a quick response to targets of opportunity, right? So if you have, a new radio that you want to fly and test, you have a new sensor that, you're not sure about, but want to test the performance before you put it on a larger satellite. That's the utility for CubeSats, is to rapidly demonstrate different technologies and try to do science, on a smaller, quicker platform, because the Landsats stay up there for decades, and those sensors, by the time that we get them, are 10 years old already. And so having the way that there's a new iteration of iPhone every other year is kind of the kind of way that we think about CubeSats, where we have new iterations of all the subsystem developments, the propulsion, the communication systems, everything that we can, just newer, smaller, more powerful. And they're replenishable. So, if something fails on orbit, that's okay. You can, have another one, similar to Planet Lab, who have hundreds of satellites on orbit. And most of them are 3Us, is that, if they fall out of orbit or they don't work, you can always send up another one to replace with, quicker parts. And so, it really gives you, with the launch opportunities, we have better opportunities to develop, scientific research, engineering, and particularly project management. So here I'll show KickSat 2. I don't know if you guys are aware of this. It started as a Kickstarter campaign, but this was at Stanford and NASA Ames. And so the overview is basically, we were meant to test 105 Sprite chipsats to demonstrate tiny, massively distributed satellites using commercial off-the-shelf technologies. So basically, the whole thing is a 3U. The motherboard is on the order of $200, and the sprites are on the order of a couple bucks a piece. And each one of these sprites had a radio in it, and they were powered by the sun. You can see the little solar panel here. And here's the deployment mechanism here. And so The utility of this was just to show that you can distribute these chipsets, that they'll work, that they'll communicate with each other, do some mesh networking, and communicate back to the mother spacecraft. And the ultimate goal for something like this is to have distributed sensor systems, so that when you're kind of distributing these in the atmosphere, say around Mars, you'll get a nice distribution of the area rather than a single point what a satellite would typically do, right? So you understand the varying distributions of the science measurements over space and time, which is actually quite interesting. You can see we did a bunch of integration. So you can see the motherboard on the left, and we had conformal coding, and we assembled the spacecraft. The Sprite is just considered one of the these little satellites. It's a single PCB with two solar cells on them and a radio and a tiny microprocessor. So we consider a Sprite kind of the child of the mother spacecraft, as you can see here, and it basically acts as its own satellite, just a teeny tiny satellite. So here's our deployment mechanism. And so we did a bunch of testing. This is vibration testing, and we had our deployment testing. So you can kind of see a sequence here of in gravity, all the chips more or less fall to the floor, but with no gravity in space, we expect them to fly out, but you can kind of see them piled up on their different sides as they're distributed. So this is us at NanoRacks in Texas, integrating the spacecraft into the dispenser, and we got to sign the dispenser door. And so we integrated onto Cygnus NG-10. It was a resupply to the International Space Station. And so it launched in 2018 around Thanksgiving time. So we actually docked on the exterior of the ISS for about 3 months. And so you can see here this little gold door. That's actually the door that we signed, and that's kind of where we're sitting. And so basically there was a bunch of supplies to the International Space Station up to resupply, and then we hung out for the 3 months, and then the astronauts filled the Cygnus with more or less their garbage. The Cygnus released and went up, deployed a few Cubesats that were also in the can with us, and went below the space station and then deployed us because they were concerned about all of our chips running into the space station and damaging the space station. So they deployed us below the space station. And then after we were deployed, then the Cygnus re-entered the atmosphere. So as far as testing for the spacecraft, we went on the ISS. So GEV standards are kind of the worst case scenario. Usually you do 14.1 G RMS, but when you go on the space station, you're kind of on this softer ride. So it really determines what your launch service provider requires you to test at. And typically when you go to the ISS, it's a much softer ride. So we didn't test to GEV's standards because we didn't need to, and we really didn't want to, overexert the satellite if we didn't need to. So you can see us doing mission operations. This is the dish over at Stanford Research Institute. And so it's a 60-foot dish. And since the sprites were so small, we really wanted to make sure that we heard them. So we were able to command and deploy them. And actually, you can see the sprite transmissions. The top two are just the sprite transmissions. The sprite mesh networking. And the middle section is actually the just the regular sprite transmissions. So it was actually a mission success, and a few papers have been pushed out for that. And so now comes VREX. And so as far as the overview for this one, so this one was, you kind of notice the same players. Zachary Manchester, he had just moved from Stanford when we completed the KickSat-2 mission to do the VREX mission. And so our orbital debris group kind of got a little bit upset that we flew, that we deployed so much what they considered debris. And so they asked us not to do that again. It was a great demonstration, but they don't want us to, create lots of more debris. So they told us that, you know, if you're going to fly anything, don't fly anything smaller than 1U. So we said, we got it. And so we basically, this is kind of a beefier version of what we had demonstrated with CubeSat. So taking a lot of the, you know, the demonstration lessons learned from the chips and then applying them to 1Us. We had the option to do three 1Us or 6 1Us, just kind of given the configuration of the dispensers. But we decided that we wanted to we wanted to demonstrate just 3 within the cost cap. You know, we still are limited by cost, and when you have 6, you have to have 2 launches instead of 1. Or 2 slots on the launch vehicle, which cost more. So we settled with 3. So it's very, very simple. It's a single PCB with 6 battery packs, very, very similar to the CubeSat motherboard. However, we put the capabilities of the radio communications into the into each of the motherboards, and you know, did ranging and high-speed communication between the 3 nodes. And you know, it sounds simple, but actually, there's not very many. There's not very many organizations that have been able to do this and pull it off. And so, you know, it seems simple, but you know, it hasn't been done. And so actually the whole architecture for this is free and open source on GitHub by PyCubed. And so, you know, the drawings are there. You can fabricate your own boards. A lot of the libraries that are typically, you know, kind of the onerous parts of it, the hard parts of it are already done, and you use simple CircuitPython to program it, which is really, really great for universities in intro to CubeSats. So very simple concept of operations. You know, all 3 spacecraft are shoved into a dispenser together. They're not tethered. The door will open. It's like a jack in the box, and the satellites get deployed, and they'll naturally drift apart due to atmospheric drag, and begin their nominal operations. So as far as their nominal operations go, they were meant to talk to each other, talk to the ground stations. In addition, we had a bonus radiation sensor on each of the satellites. So we're actually able to take distributed measurements of the South Atlantic anomaly, where the radiation belt actually comes closest to Earth. It's like a donut, and that donut kind of is like a little off-shifted, so it has its closest approach to Earth. And some, you know, it's an anomaly where, you know, they think that there's different high events of radiation that happen here, and it's never been measured distributively. You know, there's usually 1 satellite that goes through and just takes a single point measurement. Here we have 3 spacecraft flying through, so we understand, you know, what, you know, a lot of these are models, right? And so it's a matter of, you know, how far does this red extent go into the green extent? Well, you don't know until the next time you pass over, which could be days. Here we actually know, you know, what that distribution was as all 3 of them were flying together through the anomaly, but spaced apart. So kind of the fun part, we actually started this pre-pandemic, then pandemic hit, and we were really struggling to figure out how to do things. So you can see we basically started in what we have as our space shop. It's a machine shop. A few of us were just kind of sitting around having some beers, trying to figure out what we wanted to do. We pitched that. It was accepted, and we had our preliminary design review, and that our critical design review, the PDR, CDR. We had our engineering development unit, our EDU. Then you can see our flight units here. And so a lot of it was me working in my friend's laundry room / workshop, trying to work on the mechanical ends. Meanwhile, our lead engineer was basically building boards in his apartment at Stanford. So you can see the Stanford clock tower here. And his girlfriend was very upset that she wasn't allowed to use the bathroom because he was baking out boards and is toasted the entire time inside the bathroom because it was well vented. But anyways, you know, pandemic kind of slowly, you know, it got a little bit better for some time in the spring. And so we were able to go in and build our flight units. And so we built our flight units, did some range and ridge testing. You know, our spacecraft is all about communication systems. And so we actually, you know, got to beautiful mountainous California. There's a big valley. So we just stand on 2 different mountains and, you know, you can see San Jose here and do range testing. And so we did some ridge testing. We did TVAC testing. This is thermal vacuum to go hot and cold as if it was gonna go in space. We did it for 1 unit, assuming that we would apply it for 3. So that was really fun and always scary because you kind of close the door and hope for the best. And that we had some record wildfires in California last year. So the mountain that we typically did our range testing in caught on fire. And so the smoke was bad for months. When the smoke finally came down, you can see the air quality was still in the 60s. We did a quick range test where we walked the satellite out and there's a bunch of reflections over the water, but this was the best that we could do here. Then we did more ridge testing. We found a different mountain. Good thing California has lots of different mountains that you can go to. And so we were at Windy Hill and the Dish out here. And after we concluded all of our ridge testing, we decided to build all of our flight units. So you can see Max, our lead engineer, building our flight unit here. And I'm preparing boards over here and doing procedures. Basically, we had to rinse and repeat this 3 times. So as far as facilities go, we actually did our testing at NASA. For students, you can always apply for grants or partnerships with NASA. There's STPs, there's satellite technology partnerships that universities can apply to that basically pair a university with a NASA center, and then the NASA center will basically help, you know, guide and provide those facilities for student-built Cubesats. However, you can always, you know, make friends with other universities that have it. So Cal Poly San Luis Obispo has their own TVAC machine and has their own vibration table. So, you know, there's a partnership that could happen there. There's also, you know, commercial facilities that are very available for people to, you know, go in. It is a little pricey, but, you know, they are commercially available if different groups have funds to do that. So we named them after the Land Before Time, Petrie, Sarah, and Littlefoot. Each of them have their own personalities. And we vibration tested at NASA Ames. So this is the Engineering Evaluation Laboratory. So you can see us doing this more or less during the pandemic. And then we did bake out. This is one of the last requirements from the launch service provider to just make sure their spacecraft doesn't outgas. You know, there's some plastics in there. So you want to make sure that you kind of outgas everything so that, you know, when you get into that space environment that you're more or less clean and that you don't outgas onto different spacecraft's optics. So that's kind of what we had here. And basically, this was our team. It was 3 people. And, you know, we completed. And then we were on board SpaceX Transporter 1. So you can see these Starlink satellites below, and there were 143 satellites on this entire launch. And so we were actually not on the stack. We were a secondary, so we were at the aft of the second stage, which is basically this goes on top of a fuel dome, and then we are kind of attached to the fuel dome, closer, you know, economy class next to the second stage rocket nozzle. So this is launch. We were delayed a little bit, but we launched on January 24th. And then we actually got contact with our spacecraft about an hour later. The first pass, it launched from Florida, and it took it about an hour to get over, for it to pass over California. We set up our mobile ground station in the hills and actually received the packets almost immediately, which is pretty great. And that, you know, we're still doing mission operations now. We had to actually stop a little bit because we worked on a balloon campaign. So you can see here, you know, we decided to, we had some additional funding to do a balloon campaign. So one of the things that I talked about before was, you know, 3 versus 6. We really wanted to do at least 4 nodes so that you can have kind of a more global mesh networking, right? You want to really demonstrate that you can talk to very many of them. So I wanted to do it at least 4, and we were actually able to do 5, except on a balloon. So we took the same principles, and we had 1 unit attached to the balloon, and 4 units on the ground, as you can see here, scattered around, and so that they would do mesh networking as the balloon would fly over the different nodes. And so it's actually a really great suborbital demonstration of something was on orbital, and vice versa. Typically, people do suborbital demonstrations to show that kind of work in a near space environment and then go orbital. But this is actually pretty fun. We did this actually in March of this year, so last month. And so we did a bracket pull drop test. So you can see here, this is kind of what our spacecraft would be mounted into. We 3D printed this bracket. We weren't sure whether it was going to survive because it gets very, very cold when you're on a high altitude balloon. And so we were concerned that the bracket would snap upon liftoff. So we decided to do some ad hoc testing. So you can see in the middle that we actually threw the unit off the roof or the stairwell. It had a improvised shock testing as it hit the wall, which was unexpected, but it survived and actually turned out pretty great, and it gave us a lot of confidence that the bracket would survive. And so you can see our flight unit in that bracket on the far left. And these were the ground units. So we took the same, PCB and battery stack that are in each of the satellites, and actually just gave it a bigger honking antenna so that we can close the link and make sure that the communications would be good. And we had our dress rehearsal here, and so we had our test engineer walking around, Lion King, the test unit, simulating the balloon, and we had a bunch of our other test engineers scatter around the field, making sure it worked as we expected. So everything worked out well. We flew to South Dakota in March. It was very, very cold. And so we got there, set up our ground stations, basically packing all that stuff, taking it on an airplane was very tedious. But we arrived, set everything up, started doing checkout testing. We did some assembly. And so we decided to kind of pack. We were concerned about the spacecraft being so cold, especially particularly for the batteries. So we decided to kind of pack the sides with a little bit more foam and add a foam exterior to protect, this antenna. Basically, as the spacecraft as the balloon lifts off the ground, there's a potential for the balloon to go sideways and drag the payload on the ground. And we didn't want it to snap off this antenna. So we decided to put it in a little enclosure and hang it from the top. So if the enclosure looks familiar, it's because we went to Walmart and got a beer cooler for $2 and installed it in there. And this is kind of what it looked like. We just kind of installed it upside down. So this is what it would look like during the flight. So very fun improvisation, and Walmart has everything. And so we did our indoor. The weather in South Dakota was cold and windy that day, so we weren't able to go outside. So we improvised and did a EMI EMC test, electromagnetic interference test inside the hangar. There's going to be a bunch of reflections and weird RF stuff that would happen in there, but if it worked in there, we would most likely see it work outside during better conditions. So you can see us see the unit down here, and then the next day winds died down, so we're able to do the test outside. So the flight control unit actually would be what controls the balloon, and that we were hanging by a paracord down here, and that's kind of why we threw the satellite off the stairwell with a piece of string, because that string was to simulate the paracord here. And so we completed that. It was very cool to do that test because our flight service provider also does autonomous tractors. So they develop and test autonomous tractors. So it was pretty interesting for us to stand around this field and then see the giant autonomous tractors just kind of driving around us, hoping that it doesn't hit any of us. But that's pretty neat. The next day, it snowed, so we canceled operations for that day, and we did planning instead. And so, we looked at Google Maps. Our comm engineer, Cedric, actually set up a mobile app for us. We called it the Cedric Express, so that we could flag everyone, figure out where everyone is, and see where they are and log all of their information as they were to fly around. So, we planned for our ground stations to be scattered around. They have an A location and a B location further out. And what you see in the orange is the flight, the predicted flight path of the balloon. And so there's lots of Google Maps and looking at Google Earth, trying to figure out where would be a good place to set up. Next day, we didn't have our radio license yet. So we just went site scouting around South Dakota, Iowa, and Minnesota. So you can see us here. It's actually the corner of those 3 states. And so we got in our Jeeps and just kind of roamed around and off-road. That was pretty fun, and realized, there are a few nuisances that we should consider when setting up our ground stations. And so then came our flight campaign day, nice 5 a.m. to sunrise. So it was very cold and very early, and our team was very groggy. So basically, Cedric and I headed out to the balloon site, and the 3 other guys headed out to their respective sites along the flight path. So you can see the flight control unit down here with the payload down here attached via this paracord. And so the balloon was blown up, and basically as the balloon gets lifted up, as you can see here, basically it would pull up on the flight control unit and then kind of pull up on the payload unit down here. So, if there was a shear wind that came across, basically the payload would have dragged on the ground. And so here's our ground, one of the pictures of the ground station for the guys out in the field, frozen field. And you can see at liftoff, we were able to communicate with the satellite. It was very, very cold. And we kind of saw a lot of the app working, the satellite, the location of all the guys live. It was actually very, very great. So it's another highlight on the app, and kind of how far we were able to get, on the order of 180 to 200 kilometers for each of the units. So then, we had our flight at 100,000 feet for 2 hours. We got all the data that we needed. So then it was time to bring the balloon down. So that flight control unit has the ability to cut the balloon. And so we had no idea where it landed. And so it took a little while for the ground ops guys to get eyes on the balloon. There are not that many trees in Iowa, but it happened to land in this gentleman's tree. We were very, very concerned because you have to request permission to go on someone's land to retrieve the balloon. And so it was covered by this truck over here. So it took us about 30 minutes to get in contact with the owner. I'm pretty sure he was very surprised to have someone trying to retrieve a NASA payload from his tree at 9 a.m. And so they gave us eyes on the balloon, and it just so perfectly happened to be that, the parachute landed in this tree, and basically our payload actually just 2 feet from the ground, pretty much unscathed. We were expecting that our payload would hit the ground in some cornfield and be obliterated. But the fact that it landed here was actually pretty miraculous. And so we were happy to retrieve our payload back in one piece. So it did take them about 6 hours to drive back. So we called it a day, went to the bar, and came back the next day. The spacecraft actually was in perfect condition. The cooler actually, in pretty good condition, considering, I was flying at 100,000 feet. Here is the balloon remnants. They do have to go up and pick out the trash. So this is the balloon, that plastic that filled up the whole bed of a truck. And this is our flight control unit with that parachute that you saw got stuck in the tree. We basically packed everything up, and unfortunately the cooler didn't make it home with us. But in general, you can see this is actually logged data of the balloon path in the orange, and the path of all of our ground units along the ground. And so it's actually pretty neat to see everything come together. We actually weren't expecting the balloon to go past the I-35 right here, and that's why kind of all of our guys stopped before the I-35. However, the winds were pretty fast, and they wanted to make sure that they terminated the balloon, more or less in the middle of nowhere instead of on top of the town. And so they let the balloon go a little bit further, which actually gave us a lot more data. You can see the ranges here, and so the interesting part is, what you see in purple is actually, from the launch site. So that's kind of where we got the furthest distance, right? Because Cedric and I stayed at the launch site, and these are the other guys' flight, ranges between the balloon and their units. And this gap between here is actually when the guys packed up the spacecraft to move from location A to location B. So we obviously didn't get any data there. But the interesting part is this dip of when the balloon is over the horizon and it's at a longer distance, as it goes directly overhead, it's at its shortest distance to the ground unit. So that's kind of why you see the little dip here. And it was actually pretty neat because a lot of the guys did report that they had visual eyes on the balloon. It was a beautiful, clear blue day, and they could physically see with their naked eye the balloon floating overhead, and got some pretty great data with that as well. And so they moved to site B, and you can see, the little dip where the balloon kind of passed kind of a little bit more on the limb, but a little bit overhead, and kind of more or less got out of range after the balloon was terminated. So you can see the 30-kilometer, 100,000-foot float here, and then the drop as they terminated the balloon. So actually got some pretty good range data. All the radios worked up to 380 kilometers, which is more than we expected. We actually we didn't expect such a good link for what we were given. And so that's, sorry for going a little bit over time, but otherwise, we have lots of other projects at Ames, lots of deep space, science-based ones, more laser communication ones, thruster technology propulsion ones. So, there's lots of things that we do that are spacecraft and also things that are not spacecraft. We do human biology experiments, we do wind tunnels, we do models, we do a lot of aeronautics. So, NASA isn't just space things. NASA actually does almost everything, air traffic management for UAVs and all that stuff. So it's a really exciting place to work and learn about new things and be part of, exciting research. And that's particularly why I love being at Ames and doing the things that I do. So if you have any questions, please feel free to let me know. Otherwise, if you're interested at working at NASA, usajobs.gov or internships. Internships are always the best way to get into NASA. Almost everyone on my teams has started as an intern. And particularly a lot of the missions that I talked about are actually through the SmallSat Technology Mission Directorate Small Spacecraft program. So if you're interested in kind of a lot of the more exciting CubeSats that are going to the moon and doing all these crazy things, feel free to take a look there. Thank you for your time. I really appreciate it.
Thank you, Anne. Thank you, Anne. That was a great presentation. We are all literally impressed. Okay, we're still assimilating the knowledge that you put out there in half an hour time. So that was really exciting. And can you tell me how much exciting or fun is it to work at that place?
It is really, really fun. I work for the government, so I definitely don't get paid as much as everyone else in Silicon Valley. But just being able to work on new and exciting things, the most cutting edge technologies at the fast pace that we can is really, really exciting. And I really do enjoy it, and it makes everything worthwhile. And even for, a lot of our contractors is that everyone loves what they do. And being surrounded by everyone that has the same kind of passion as you, and a lot of, the teamwork that it takes to put these things together, it really has a camaraderie and, working towards a really fun, exciting goal.
Excellent, excellent. We have few questions here for audience. Please post your questions for Anne here, and we'll try to answer them one at a time. And before you answer the question, I want to ask you. We have a lot of young, smart kids here. So, what is your advice before they take on a project, or if they want to get into a path that you have followed? What would be your advice?
So, for those that are still in university, I would say join the CubeSat University team. That's probably the best way to get experience and learn. And take internships, and honestly, you know, be willing to do things that you're not comfortable in doing and challenge yourself. You know, you never know where you're going to get and how far you can go. And you know, when I first did my PhD, I actually wasn't intending to do any spacecraft. I was actually thinking about doing UAVs. And an opportunity presented itself where I said, sure, I'll look at this control system, and actually ended up really loving it and having a full career out of it.
Excellent, and that's a great advice. I also try to say this, like do things that you're not comfortable. So that's a great advice. When somebody like you come and talk to our students, that means a lot. Thank you so much. Let me get into the questions here. So Patrick is asking, were the GEVS standards used for vibration testing?
Yeah, so I addressed that while we were talking, but usually GEVS is the Goddard Environmental Testing kind of gold standard document. So usually you test to that as kind of the you know, maximum predicted, and you know, it's usually 14.1 GRMS. However, when we went to the space station and they said that, you know, this rocket is a lot softer, you only need to vibrate it to 8 GRMS. So it really depends on your launch service provider. But you know, if you work with your launch service provider, you can actually get a lot lower levels. But you should always design to GEVS. All
right. So we have our next question. Abraham Rodriguez. I think he's working in the TitanSat CubeSat team. So his question is, what vibration and TVAC testing facilities do you recommend for students building CubeSats? Or are there any useful programs to analyze? Yeah, so it really depends on where you are launching from. If you're launching from the International Space Station, there's going to be a lot more requirements as far as testing goes, particularly for your battery system, since there are humans on the International Space Station and they need to have that extra level of safety. However, if you're just going on, you know, a SpaceX, you know, rocket, ride-share rocket that has only satellites on it, you know, you don't have to do as much rigorous testing. And so at a bare minimum, typically for, you know, things like SpaceX rideshare, you need to have UL listed batteries. So always get UL listed batteries when you're speccing out your EPS system. It's just a standard and makes life much easier and documentation much better. Typically, your requirement is to bake out a bare minimum, but I would say definitely TVAC your spacecraft. That's where you go thermal, hot and cold cycles to your predicted environments. You know, a lot of people end up skipping that, and that's where you find kind of the earliest modes of failure, and just going super hot and super cold. That really is, you know, it adds some time to your schedule and is a little bit costly, but it's completely worth it because you really figure out what the issues are with your spacecraft during that time. You know, you close the door and you don't, you know, you can't touch it. And so that's kind of how it is in space, right? Once it's up there, you can't touch it. What do you do? And that's a good exercise there. And vibration testing is always required. It's just a matter of what levels depending on the launch that you have. So yeah, hopefully that answers the question. Yes, yes, Anne. I'm very impressed with the way you're packing so much words into one minute. That's very just like CubeSat. You got the CubeSat way of talking. That's impressive. Yeah, sorry, it's a lot of acronyms. All right, we have Kai, right? And for your information, Kai and Patrick, they are two of our students in the CubeSat team, the TitanSat team. They got selected for the state level research competition, and they are going to have their final competition next 2 weeks from today. Great, that's awesome. If you guys need any reviews, let me know. Sure. So Kai has a question: how much did it cost to ride share your 3U with SpaceX? Right, so we were actually at the aft economy class. So for a 3U ride at the aft of the fuel dome, it cost us on the order of $150,000 for a 3U CubeSat.
If you wanted to be on the top of the stack where the rest of the other payloads were, I imagine that's a little bit more, but we get the kind of government discount. But generally, I think that SpaceX was advertising that is on the order of $5,000 a kilogram per cube, or $5,000 per kilogram. So if you wanted a ride share, you should definitely a cheap ride share. You should definitely talk to SpaceX.
Perfect. We have one more person here, Steven Sykes. He's asking, some like advice question. So what I was thinking of making a CubeSat as a payload for the rocket project. So would you recommend a sprite size as a proof of concept as a working payload?
So I guess, is this a suborbital rocket or?
Steven, can you clarify the question? Steven, if you can hear me. Can you unmute and ask the question? Yes, and yes, that's what he meant.
Oh, okay. So we've definitely seen people wanting to actually deploy. So the concept is that you go to Mars and you scatter these little CubeSats around. Then they float through the atmosphere and they take measurements and just kind of sit on the surface after they've kind of made it to the surface and give you distributed surface measurements. So we're actually trying to pitch that has been pitched from another group to fly on Blue Origin's suborbital rocket. It just kind of hops up and spits out some CubeSats and comes down. I think that it's great. I think it's just a matter of, do you plan to eject it from the rocket or do you plan to keep it inside the rocket?
All right, so we have a question from Faraj Haddad, and he's asking if you are interested and if you want to get a ham radio license. A lot of ham or HAM radio clubs have their own CubeSats. So they are working on to send to space. There are different ways to get involved. I think he's just giving a comment. Thanks for it. Thanks for the comment. Any more questions?
We actually rely on hams a lot to get a lot of our beacon packets, and I think it's really, really great, especially if you're part of a university. If you're part of the university, there's usually you can get your licensing free through the clubs. However, if you don't do that, then when you go into private sector and you're no longer a university student, it does cost money and it is expensive. So I would say definitely get your technician's license while through your university if you can.
John, you also saying something?
Yeah, I think Kai had a question. She said, how often are you able to use COT parts? I think, do you mean COTS parts, like commercial off the shelf, or is that something different?
Yes.
Yeah, so as far as commercial off-the-shelf parts, basically everything that we do is commercial off-the-shelf parts. For a lot of the CubeSat programs, we're allowed to, and we're not in space for very long, and so we have some really quick missions. If it lasts a year up there, we'll be happy with that. And we've definitely built CubeSats that are still up there after 2 years based off of all COTS parts. And it still works. Everything actually surprisingly works. And so it is much cheaper for us. We buy a lot of stuff on DigiKey and Mouser and McMaster. And so that's the value that brings to us. Whereas, if you had a lot of the higher class missions, you would have to get radiation tolerant and radiation hardened parts. You would have to have reliability in these parts, so they would have to be tested to death. And if you need to test them, then they cost 10 times as much. So our normal processor that costs what, $40. If you test that, then that whole processor becomes like $100,000 space rated processor. And so I think the thing is, for COTS parts, it's useful to see what other COTS parts other CubeSats have built, and know that these other CubeSats have built it, and just check the temperature ratings and the vacuum ratings for all these COTS parts to make sure that they're appropriate for the environment that the CubeSat will be in.
All right, and we'll take one more question. We have Professor Dinah Bain from computer science. So she's asking, what computer science projects can be done to develop the CubeSat?
Oh, so there are so many interesting things that we're doing now. So the value of the computer science folks are, FPGA FPGA development. We're always looking for FPGA engineers to basically, have efficient routing for our spacecraft. One of the biggest problems is that we have a bottleneck where we have these really high performance, systems like a hyperspectral imager, and it's just sucking in so much data, and it needs to be piped out and processed. And to get those, level 1 and level 2 data products on the spacecraft, because it's hard, to downlink all of the level 0 raw data takes so long. And so just those high efficiency programming and high efficiency program that you can do on orbit, because you are really power and thermally constrained. And so, working on GPUs and high processing systems, you can also do attitude control systems. A lot of that is just, controllers, and even, mesh networking for kind of the things that I showed for CubeSat and VREX. I think that there's so much utility in computer science in space, because that's pretty much what's running all of our, keeping our spacecraft going. And you can never have enough flight software engineers on your project. I have 4.
All right. And I think we need to move on to the student club presentation. So thank you so much for giving this wonderful talk. It's inspiring, and this means a lot to us. We hope you can come back in the future as well. We really want to have this engagement with NASA's Ames Research Center. So thank you so much.
Thank you so much. Yeah, thank you for having me. I really appreciate all of your time.
Would you be kind enough to stay a little bit, maybe 10-15 minutes longer to hear from Patrick?
Definitely.
All right. I know some of you have more questions, so you can always post the questions in the chat, and maybe Anne can type the responses in the chat. But let's move on to the next segment of this event, and that's a presentation by the TitanSat student organization. Patrick, Kai, can you hear me?
Yes, I hear you loud and clear.
All right, Patrick, thank you so much, for connecting us with this wonderful person. We are so impressed. All right, if you can share your screen and.
All right, yeah, I have permission now.
Yes.
And let's see. All right, here's my screen.
For all of you, we won't take long, maybe another 30 minutes. Okay, so Patrick and Kai have a very short presentation on our TitanSat student organization and the project. And also we hope you can join this organization. Okay, this is a great platform for a multidisciplinary, and this project is extraordinary. Okay, that's what one word I could say. Patrick, the floor is yours. Please go ahead.
All right. So hi everyone, I'm Patrick Babb, and my co-presenter today is Kai Rai. As you see here, our project is the Titan Wildfire Infrared Prevention Satellite TWRPS CubeSat. Kai Rai and I are both undergraduates working on this project here at Cal State Fullerton. All right. So wildfires are an issue, especially in the Western United States. And since 2012, there has not been a month without a wildfire. Climate change is contributing to this problem, and California especially is in need of better wildfire management.
So how wildfires can currently be detected and monitored is with the Fire Information for Resource Management System, or FIRMS. And this is a sizable array of satellites, most of which are really intended for climatological observations, can naturally be used for wildfire tracking. And this image is an example of what FIRMS is capable of. And the map is spattered with a bunch of thermal anomalies, and 4 of these happen to be wildfires. You can tell by the plumes of smoke. These satellites are astronomically expensive to build, launch, and maintain. So what if we could make this more affordable and accessible for people other than just NASA and Raytheon?
Our research aim is to fabricate a CubeSat that provides a less expensive way to monitor and predict wildfires with the same utility as FIRMS. As we know here, CubeSats are miniature satellites used by a variety of organizations such as universities. And the CubeSats typically operate in low Earth orbit and can be equipped with specialized equipment to monitor and predict wildfires, although they don't have to exclusively operate in low Earth orbit. Our satellite is equipped with a long-wave infrared imaging camera, as seen on the left, and it's capable of detecting evapotranspiration. Evapotranspiration is the process in which soil and plants release the moisture to the atmosphere, resulting in reduced temperatures due to the evaporation. The camera can detect this temperature difference and our CubeSat can then figure out where the moist and dry spots are located on Earth for better fire prediction and tracking.
So these are the most general specifications that our CubeSat's going to have. It's going to have 3 units, abbreviated to 3U, so 10 by 10 by 10 centimeter cubes, each cube being 1 unit. It also must withstand the harsh conditions of low Earth orbit. I think we got some of those, an idea of those conditions from Onwin. And these design constraints we mostly got from NASA's CubeSat 101 booklet. Our satellite's going to feature deployable solar panels, an antenna system to relay imagery to ground stations, a far infrared imaging camera that can produce imagery capable with comparable to firms, image processing and data analysis software that we're going to have to program ourselves, and an HD camera to produce images for the visible light spectrum. Before we got started, we had to do a lot of research, and one of the more noteworthy things we intended to determine was the approximate orbital decay time for an intended orbit. With some light calculations, we came up with a rough estimate of between 1 and 2 years. The graph here is directly taken from one of the studies that we were heavily referencing for our calculations, and it displays the relationship between orbital altitude, mass, and decay time.
This satellite's intended operation is to operate at 51.6 degrees off the equatorial plane at an altitude of 400 kilometers, the same orbit as the human-operated International Space Station. 400 kilometers is about 250 miles. This orbit was chosen because it is representative of orbits by other CubeSats under NASA's CubeSat launch initiative. We also created a free body diagram of the CubeSat to understand its rotational dynamics. So if we just look in the plane of the page, we see that on the left, the torque generated by the magnetorquer on the CubeSat is equal to the magnetic moment vector crossed with the Earth's magnetic field vector. In this case, we see a counterclockwise torque generated, resulting in a counterclockwise rotation about the center of mass of the CubeSat. Oh, Kai, you're muted.
So we started our design process with a design matrix, a kind of comparative analysis between competing design concepts. And the table shown is just a truncated example of the design matrix that we used for our satellite skeletal design. And each of the 5 factors are assigned a rank between 1 and 5. And then all the factors are summed up at the end for comparison. So moving forward with the design that we selected, we wanted 2 prototypes. We planned for a low fidelity prototype made from PLA plastic and 3D printed, and a higher fidelity prototype machined from aluminum. On the far left is a picture of the CNC machine available to us for all of our aluminum fabrication needs. In the middle is a picture of a tabletop wood CNC machine that we used to test out our G-code. And on the far right is a picture of the 3D printer that we were using to print one of the rails for the satellites. Shown in the picture on the bottom left is a successfully fabricated aluminum cross brace for the CubeSat.
And here we have a block diagram that's made from a series of transfer function blocks, which ultimately relate the output or angular position to the input desired angular position. So here we have a controller, our magnetorquer, and our TitanSat dynamics, which ultimately allow us to model the angular position of the CubeSat before we actually launch this thing to space. And here we have on the top right, the magnetic field model of the CubeSat as it makes a 10-degree rotation in the XY plane using net coordinates. And on the bottom right, we have our expected system response, given that we are modeling this off a second order system.
So going from left to right, we have the 3D rendered preliminary engineering model that we intend on using for flight testing in its deployed state. Next, we have that same model in its stowed configuration. And lastly, we have our low fidelity 3D printed prototype for testing the mechanical actions of the doors.
And here we have our printed circuit board created by and tested our electrical engineering student, Brad Williams. And here, the printed circuit board manages incoming power from the solar panels and power distribution to the CubeSat. The PCB needed to be custom in order to accommodate the power needs of the electrical components, such as the magnet worker and the IR camera. Data from our IR camera suggests that evapotranspiration is being observed. As we can see in the left image, we have green moist plants and dry wood chips. On the right image, we have a thermal image from the IR camera. That's the IR image. And we can see that where we have more moisture, we have reduced temperatures, and where we have less moisture or dry wood chips, we have increased elevated temperatures in the right image as seen by the white hot pixels.
Another notable result is that we calculated what the infrared camera could see from its altitude of 400 kilometers. With a field of view of 8 degrees, we were able to calculate that the resolution per pixel is about 10,000 meters squared, or 100 meters across. We also determined what the viewable area in all our images will roughly be, 3,130 kilometers squared, so about the size of Yosemite National Park. A significant driver behind our project is its costs. So we did a rough cost comparison between one of the satellites in FIRMS, which is the Joint Polar Orbital Satellite, or the JPSS. The contract amount for 2 of these satellites in 2018 was about $1.1 billion. On the right, we have an itemized price list of our CubeSat, which comes out to $157,000, which is 7,200 times cheaper so far. This is because it's been specialized and miniaturized for our mission goals. And I know I'm not quite comparing apples to apples here, but I wanted to show that the main idea is we're cherry picking what we want from the suite of instruments you see on the left, and we're trying to fit it into something the size of a lunchbox.
Our next steps include a high altitude balloon test in order to test the ground resolution, our wireless communication speed, and our thermal insulation as well.
So the intended impact we have for our project was to really be a useful aid for California and its goal to treat nearly 1 million acres of land annually in order to reduce fire hazards. We also see some potential in gathering climate data like ocean temperature change and deforestation.
And here are our references, as well as some people that supported our project. And thank you for listening to our presentation, and we look forward to answering any questions you may have and talking further about TitanSat and the student organization. Thank you.
Thank you, Patrick. Thank you, Kai. I just want to request Patrick and Kai if you can give your contact email in the chat so that students can reach out to you for joining the TitanSat.
Yes.
Those who perfect. Kai, thank you. Thank you. Any questions from the audience for the TitanSat team? All right, we have a question from Anne here. Patrick, I'll just read it out. What are your key upcoming milestones for your balloon test and the CubeSat project?
Yeah, so for the balloon test, we really want to see if we can line of sight send images from 100,000 feet. We've been making incremental progress in doing 1 mile test for a transfer of an image and 2 mile test. And now we're trying to do a 5 mile test. So we really want to test as much as we can on the ground. And in sending these IR images from our CubeSat to the ground station. So that's one major milestone for the high altitude balloon test, really sending that image down from 100,000 feet to the Earth. And we also want to understand how long that will take as well. In addition, we also would like to understand exactly how our system will operate in a low pressure, low temperature environment collectively, rather than only doing unit tests as well. So that's really where our altitude balloon test comes in.
All right, Brad has posted the Discord link for the TitanSat project. Patrick, can you explain like how what's the environment like working in the TitanSat team? I know you have students from all different departments. How do you coordinate all different expertise?
Right. So we operate on the Discord and we meet every Tuesday. So really anyone can ask a question any time of the day that they would like. And currently we have about 41 members from Cal State Fullerton on the Discord. And the environment is very collaborative. We have electrical engineering majors, mechanical engineering majors, computer engineering majors, and computer science majors on our team. And it's not like a CubeSat or TitanSat Lite. It's the actual thing that our members work on. So our members really support us. And so we really don't plan on having a brain drain after we leave, because the knowledge will just be transferred to the next pair of members.
Perfect. Kai, we have a question from Nick here. So Nick is asking, what is an ideal resolution for this type of project? Is it 10,000 meter square per pixel good enough?
That's mostly from our budget constraints and the camera that we inherited from last semester's team. Of course, if it could get better than that, we'd love to have it, but I think 10,000 meters squared is pretty decent for what we want to use it for.
Perfect. I think any further questions? Nancy, thank you, and thank you for helping us organize the event as well. So Nancy has done a great part in organizing this event. Thank you so much.
I actually had
go ahead.
I had a question for On specifically. I know CubeSats typically have like reaction wheels or magnetorquers or thrusters in order for the control system for attitude and station keeping. How exactly do you model that? Do you use MATLAB Simulink, or do you use a different type of software?
Yeah, so for attitude disturbances, we typically use MATLAB and Simulink, and basically we develop our own simulations and we update them as needed with our controllers. And kind of an easy way is that you get to port it to flight. It's not efficient, but what we actually do is take the flight code, that we develop on MATLAB and Simulink, and use the MATLAB C code converter, the built-in converter. It's a package, and it converts over C code, and we kind of load that on our spacecraft as kind of like a quick and dirty. But it's not very efficient. So we're actually moving to verifying the controllers on MATLAB and Simulink, and then converting that over to native C to run on our low-level microprocessors. It's hard. Developing a simulation like that is definitely some people's high-level simulation like that is part of people's thesis. So I would say STK has a package that you can use. It's called Solus, but the thing is it's very expensive, and it doesn't work for kind of off-nominal situations that, how long will it take for my satellite to recover from, a high rate of, tumbling that it has. Basically, that one is more of the, it won't solve that problem for you. Basically, the solution diverges. And so you still need something custom for answering the question of how long will it take for me to detumble from 5 degrees a second upon deployment. But in general, everyone ends up always doing their kind of more or less in-house solution simulation. And I imagine that if you guys have at least one person to do that, and you guys can use that as a tool that you guys can have for kind of the remainder of your project for other projects if you decide to do other ones. Actually, I have a question for you guys, is that there is a very large NASA and maybe it's like NOAA or USGS initiative to fund projects like yours for managing wildfires. Have you guys applied to any of those grants and requested any of that?
And I will answer that we are in progress. We are currently working on it, and we will be requesting funds this year. Okay, last year we tried, we narrowly missed the deadline for submission. So we are going to do it this year. Yeah.
Okay, I think
we are somewhere aware, but we will definitely need more information. We'll reach out to you as well for more information. Yes, we are working on it.
Okay.
Definitely. Thank you.
Yeah, this is a great candidate for those style of grants, and if you guys are cost constrained, this will help.
Definitely, with your help.
And give you the guidance that you need from NOAA, USGS, or NASA as needed.
Perfect. We have one last question. Anybody can answer from either Anne or Patrick or Kai. Can you utilize the same tech used on the Mars Perseverance to grab photos and recognize safe and non-safe areas?
That's something I don't think we've considered yet. We haven't gotten as much progress in the computer science field with this project yet. But we do plan on further development on any of the programming aspects of the project, future semesters.
Perfect. I think with that, I don't think any more questions. So I hope the audience enjoyed the event. It was a lot of information for a Friday morning. And I want to thank Anne for coming and spending time with our students. Patrick and Kai, a great presentation, and good luck with the final of the student research competition. So with that, I think we will conclude the Tech Talk events, and we will be conducting more events in the future as well. So I hope you will all join and have a wonderful weekend and a great closing to the semester. All right. Thank you all for joining. Thank you, Anne. Thank you, Patrick. All the faculty who joined, thank you so much. All the students, thank you so much.
Thank you, Sajil.
All the stuff.
Great as usual.
Thank you, Donna. Thank you so much. All right. Please reach out to Patrick or Kai if you want to join the student club, TitanSat club. You can always reach out to CCRPD. I just posted the email. Hope you all enjoyed. Thank you so much. John, I think you can stop the recording.
Okay. Have a good weekend.
Yes.